Okay, welcome. We are talking about sublimation today, starting off. So, sublimation is a phase change. It's maybe a weird one. It's when solid directly goes to the gas phase, completely skipping the liquid phase. And not all substances can do this. Substances that sublime, sometimes it's called sublimate. You say sublime, and I say sublimate. Have unusually high vapor pressures. So they will sublime or sublimate at room temperature. So we'll talk more about vapor pressure as the unit goes on. So two classic examples of sublimation, substances that sublime, are mothballs. Okay, this is a really weird substance. It's called naphthalene. And you're probably familiar with mothballs as quote-unquote old people smell. Now, I know old people have a lot of weird smells like strange soup or perfume or whatever. This is a very distinct smell, mothballs. And so people used to put mothballs inside things like your closet or like a chest that would have woolen sweaters or blankets to prevent moths from coming in, laying eggs, and chewing holes through stuff. So these things give off a gas. It goes straight from that ball, that solid, to the gas, and it detracts moths, and honestly, it detracts me. It smells really gross. They are available for purchase, so if you're dying to find them, go ahead. I love how it says original scent. What does that even mean? It's gross. Another substance that sublimes or sublimates is dry ice. So dry ice is solid CO2. So CO2 solid. So here it is. And you put a little bit of water on it. And you start to see the vapors, the carbon dioxide gas coming off. But you don't get a puddle and then it becomes gas. It goes straight to the gas phase. And so a lot of times, for special effects like this witch's cauldron, you see dry ice. And that's because they will have a very high vapor pressure, which again, stay tuned, we'll talk about. The opposite of that is something called deposition. So deposition is when a gas is completely changing from gas, directly changing from gas to solid, and we skip the liquid phase. And so this is a little bit more challenging, but soot depositing in a chimney from the gaseous state. So, or a candle. So let's say you have a candle that's lit, it's been burning for a while, and then you blow it out. Immediately you see a smoke trail. And that smoke trail are solid particles in the air. Now, you didn't see those particles before because they were in the gaseous phase. And so as soon as you extinguish that flame, you get the little particles, which are solid, gas directly to solid. And the reason I mentioned soot from the fireplace is because you have a place for them to deposit. Get it? Deposit, deposition. So the solid particles that were in the air now, lay out onto the brick or wherever. And you'll notice that when you extinguish a candle too. Same thing. But there's not a puddle. There's no liquid. It just goes straight from gas to the solid. Okay? All right. Two weird words, hygroscopic and deliquescent. So hygroscopic substances absorb water or moisture from the air. So I don't know how you store sugar in your house. I used to store sugar, like a granulated sugar, the white sugar. I used to just take the bag, which is a paper bag, and I would just roll the top down. And then I'd put that in the cabinet and not worry about it. Sometimes I'd wrap a rubber band around it. But then inevitably the next time I go, I would open it up and I'd see there were chunks. There were it was like chipping away. I had to get the knife and chip away like a chisel because but the sugar had formed these solid masses. And that's because it's absorbing moisture from the air. It was not in an airtight container. So now what I do is I keep my granulated sugar in one of those OXO vacuum sealed containers. And so it keeps the air out, so it keeps the moisture out. So I don't have as many of those chunks of sugar because it's absorbed moisture, because there's less. Sodium hydroxide pellets also if you leave them sitting out, they'll start to get slimy after a while. And the reason why it's getting slimy is it's absorbing moisture from the air. But then you could go even further. You could have a substance called that is deliquescent. And that means it's absorbing so much moisture from the air that it's going to dissolve itself. And so anhydrous calcium chloride. Let's see if I can make this work. Come on now. All right. Here we go. Let's do this. So this is a time lapse. So those are calcium chloride pellets. And look at how they're kind of coming together. You can see it. Looks like, oh, wow. It's absorbing moisture from the air. So that would just be hygroscopic. But all of a sudden you notice it's just taking in so much moisture that it's starting to make a solution. It's starting to dissolve itself in there. Look at that. Pretty cool. All right, so let me make sure this is go away. Okay, so that's deliquescent, dissolving yourself in water, so absorbing from the air. All right, so now we're going to focus on gases, just gases. So we talked about solids and liquids before, and they're okay, but gases are really cool because they're affected by so many different things. So we have something called the kinetic theory of gases. Sometimes it's also, where's my pen? Oh, here we go. Sometimes it's also known as the kinetic molecular theory, which is known as the KMT. So either one. The first, and again, it's a theory, but a lot of this has been proven, so you don't have to say, well, it's a theory, so it could be wrong. No. Number one, gases are composed of tiny, separate particles. They are so far apart that the empty space allows the particles to be compressed. We've talked about that. Gas particles are in constant, rapid, straight line motion and possess kinetic energy. So when you've got a gas particle, it's not going to go, it's not going to do that. Instead, it's going to travel like this until it hits something like the wall, and then it's going to go off like this, and then it's going to maybe hit another particle, and so random straight line. We don't know what it's going to do. It's random, and it's going to be constantly in motion. Particle collisions are elastic, meaning kinetic energy, Ke, kinetic energy, does not change into another form of energy. Because energy can change forms. It can't be created or destroyed, but it can change forms. But when particles collide, as they are most often going to do, you're going to keep that kinetic energy the same. It's not going to become sound. Like when it gets hot out, you don't hear boom, boom, boom all the time. I mean, there's thunder, but that's another thing. You don't hear gas particles, making sound, or you don't see all kinds of things changing because kinetic energy remains. Molecules of a gas do not attract nor repel each other. They're just kind of there. So that's kinetic theory of gases. Why are gases compressible? We've kind of talked about this before, but just to bring it back, because gases do not have a definite shape or volume, they take the shape of whatever container they're in, they take the volume of whatever container they're in, and because they have lots of space in between their particles, you can smush them together, you can compress them. Okay. I think that's where I'm going to stop. So, thanks for watching.